Hi, my name is Javier Gonzalez. I'm a principal software engineer with Samsung Electronics, and I lead Samsung Semiconductor Denmark Research, which is a new Samsung R&D center in Europe where we focus on open source, ecosystem, and architecture for next generation SSD interfaces. I'm happy to be part of this OCP Technical Symposium, virtual edition. Sure, it's very different from other years, but still plenty of fun. So today I'm going to be talking about zone namespaces real quick. I'm going to touch on the use cases, go a little bit about the standard, and then the Linux ecosystem. So it's still a very relevant question. Why do we need a new interface? SSDs are already mainstream. They have great performance. They're easy to deploy, and the price range is becoming very, very acceptable. But we still have three main challenges that we're working on. The first one is how we reduce the write amplification and the over-provisioning to provide customers with the most out of the NAND that they're purchasing. There are different ways of doing this. By changing the interface to the SSD, Hi, my name is Javier Gonzalez. I'm a principal software engineer with Samsung Electronics, and I lead Samsung Semiconductor Denmark Research, which is a new R&D center in Europe where we focus on open source, ecosystem, and architecture for next generation SSD interfaces. Happy to be part of this OCP Technical Symposium virtual edition. Sure, it's different from other years, but it's still plenty fun. And today I'm going to be talking about zone namespaces real quick. I'm going to touch on the use cases, go a little bit about the standard, and then talk about the Linux ecosystem. So it is still a very fair question to ask why we need a new interface. SSDs are already mainstream. They offer great performance. They're easy to deploy, and the price range is coming to a very acceptable price. But we still have three main challenges. The first one is how we reduce the write amplification and the over-provisioning to give customers the most out of the NAND that they're purchasing. There are different ways of doing this. Modifying the interface to the device is one of them, and this is where CNS is playing a role. The second part is how we reduce further the total cost of ownership. Sure, we are working on increasing constantly the bit count on the NAND side. Now there's one in QLC. By modifying the interface, we can play with things like reducing the DRAM, and as I mentioned before, reducing the write amplification and the over-provisioning, which has an impact on the cost of the SSD over time, right? The third part is how can we run several applications on a single SSD while still providing a good quality of service. So from what CNS is to me comes from understanding two main things. The first one is what a zone is, and the second is how you write to this zone. So if we partition the LBA address space into ranges of fixed size, that's the basic of what a zone is. Then how a zone is laid out on the device, I'm going to talk on that into the next couple of slides because it targets very much the use case of that CNS instance. The second part, how you write to it, it is important to understand the concept of the write pointer. So the write pointer is the one that makes sure that we write strictly sequentially to a zone, and it moves only in one direction incrementally up until the moment the zone is completed, and then it needs to come back. To understand that, it is important to get a grasp of the zone state machine. There are many zones. Basics is the zone that starts in the empty, moves to open when you start writing to the zone, and then transitions to close and full when the zone is full. The important part here is that the transition from full to empty is governed by the host. This basically means that garbage collection and any granularity that is lower than zone happens on the host software. This allows us to basically eliminate garbage collection on the device side and allows us to bring write amplification on the device very, very close to one. So once you have this concept, we see two main use cases. One is archival, another one is IO predictability. This is the next slide. Focusing on archival, basically zones in this case lay across the whole NAND array. And this is probably the most obvious case for CNS, because it's basically about bridging the gap with high capacity SSDs and facilitate the consumption of QLC. Here, in this use case, the important thing is that you have data that is cold. You have data that you have pre-processed probably in other SSDs or in a cache layer, so the data is semi-mutable. And it is important that data within a zone belongs together. So basically, you do not want to do any sort of host side garbage collection. You want to be able to have data on zone either valid or invalid at a moment in time, all at the same time. On the backup slides, you're going to see extensions to CNS and other concepts. One of that concepts is that of a pen. For this particular use case, the use of a pen is very useful because as zones are laid out on the whole NAND array or a big portion of the NAND array, you want to have several in-flight IOs going to the zone so that you're not restricted by QDIP1. I encourage you to look into that slide after the talk, this slide. And this, from an architectural perspective in this use case, since zones are very big, we can really reduce the DRAM on the device. We definitely break the 1 GB per terabyte, but since we have like hundreds, maybe thousands of zones that are very big, the mapping table is very, very small. The second use case, which is less obvious, but where we are, a use case we're very excited about, is that of IO predictability. Here, it's not about having a zone that is laid across the whole NAND array. It's about having zones that are groups of zones that are laid into small portions of the NAND array. And we're trying to refer to this as isolation domains. And the important part here is that zones or these isolation domains, groups of zones, can be used by different applications, and the device is offering a certain level of guarantee on how these isolation domains behave. So basically, you can run different applications on different of these isolation domains and get a good level of quality service. Basically, we're targeting multi-tenant environments where the host is the one in charge of this data placement on the isolation domain, but also the IO scheduling, because the host has the visibility over these isolation domains. You may ask, what's the cost in terms of RAM amplification and over provision and DRAM? The good thing is that these properties are intrinsic of CNS. So we are still reducing this. We have more zones. The mapping table is slightly bigger, but we are already breaking this 1 GB per terabyte. So the cost is still very, very low. This use case, you can combine with the archival on different tiers of your storage. And it's not necessarily targeted to QLC memory. We can use other faster memory in this case. And for this, I would encourage you to look into these backup slides. That is these random error caches that we're nowadays standardizing on NVME, and also the concept of a simple copy, which is already ratified on NVME, which basically allows us to offload copies from one zone to another without going through the host CPU. This becomes very, very relevant when an application manages different zones and wants to move data to do the host-assisted garbage collection. In terms of a Linux stack, we are building on top of the existing Zoneblock ecosystem that many companies have been building through time on Linux to support primarily smart drives. Big kudos to WD, Damien, Seagate has been working on this, Suse has been working on this, Hannes, very awesome work. At this moment, we are extending this framework with CNS. I'm going to walk you very quickly through the stack. we start at the emulation level. We have a full QEMU extension for CNS, so that those that do not have drives, especially research institutions, can get started. At the NVMe level, we extend the NVMe with CNS. This is kind of an easy change. We also have a number of changes to the block layer, because even though some devices are already there, it's very different to deal with hard drives than to deal with SSDs, right? We're working primarily on F2FS. I know that Christoph Hilby is working on XFS, and look forward to see that work reaching the mailing list. And then from a user space interface level, we've added support for IO ring, for libIO. We also have the ioctl for primarily admin commands. From user space, I think the flagship is something that we're calling XNVMe. Please visit xnvme.io. XNVMe is basically a library that is targeted for NVMe native applications. It allows you to run any applications either on a kernel interface like IO ring, or through SPDK without having to recompile or making any code changes to the application. This is already a thing of its own. When you are thinking that applications will have to change to deal with some namespaces, then XNVMe becomes extremely important, because instead of having to port your application for different interfaces, you could port it to a single library. Important to mention, XNVMe in this case is focused on Linux, but we're also adding support for FreeBSD, and we're in talks on adding support to other operating systems like Windows. And then, for early adopters, we have built all the libraries and all the tools that allow CNS to be usable. NVMe CLI, extended block zone, file system tools, extended block test, FIO. I know that other companies are working on this too. When some namespaces get ratified, which is going to happen very, very soon on NVMe, we are going to start releasing all this code open source, and work with the community to make sure that this reaches the mainland in good shape. Very quickly, takeaways. CNS is a new interface on NVMe. I want to remark this. I've been working on Open Channel for many, many years. Main mistake we made is we never focused on bringing it to NVMe with enough effort. This is happening for CNS, and it's very, very good for adoption. In terms of use cases, Archival is probably the original CNS use case, but we've seen IO predictability, a very important use case that will allow people that were interested in Open Channel to look into NVMe and find answers for the use cases there. The host needs changes, but I would say that building on the existing zone block ecosystem on Linux, these changes are minimal, and I would expect that by this summer, Linux is a full CNS capable if everything goes okay with the ratification. Many people is working on the open source ecosystem. Samsung is working there too. We are releasing a XNVMe in the following weeks, and we have all the work on Linux kernel, tools, FIO. One thing that I didn't mention before is we have a backend for RockCP, which we are also pushing upstream and making available as soon as we can. And if you go to the backup slides, you'll see that there's some CNX extensions we're working on. Those we're bringing to NVMe, and we're sponsoring and driving some of this work. If you have questions, you're welcome to ask now. If you have other questions, you're very welcome to reach me on email or on LinkedIn. So thank you very much, and please make sure to look at the packet slides. Thanks.